On the morning of February 15, 2013, the people of Chelyabinsk, Russia, were going about their day. Children were arriving at school. Workers were beginning their shifts. Drivers were navigating the morning commute. The sky was cold and clear, a typical February morning in the southern Urals, nothing to distinguish it from any other winter day in a city of 1 million people. Then a light appeared in the sky, brighter than the sun, moving fast, leaving a trail that witnesses described as a bright streak across the sky, as if a piece of the sun itself had broken loose and was crossing the horizon. The light lasted approximately 30 seconds, long enough for many people to stop and watch, long enough for some to take out their phones and start recording. Then the shockwave hit. The explosion, occurring at an altitude of approximately 30 kilometers, as a rock the size of a 6-story building entered the atmosphere and disintegrated, released energy equivalent to approximately 500 kilotons of TNT, 30 times the energy of the atomic bomb dropped on Hiroshima. The shockwave shattered windows across an area of roughly 7,000 square kilometers. Buildings vibrated. Car alarms went off across the city simultaneously. People standing near windows were thrown across rooms by the force of the pressure wave. Approximately 1,500 people were injured, most by flying glass. The asteroid that caused this had not been detected before impact, not by amateur astronomers, not by dedicated near-Earth object surveys, not by any government space agency anywhere on Earth. It arrived unannounced. It arrived unseen. And it was not the worst example of this problem. Not even close. To understand how a rock the size of a building can enter Earth's atmosphere without anyone noticing, you need to understand the scale of the challenge. Space is enormous. Near-Earth space, the region of the solar system where asteroid orbits cross or approach Earth's orbit, contains tens of thousands of objects large enough to matter to civilization, and a far larger population of smaller bodies capable of producing violent airbursts if they arrive over the wrong place. For the officially recognized planetary defense threshold, near-Earth objects roughly 140 meters across or larger, NASA estimates a population of about 25,000. Less than half have been found. Less than half. That means thousands of objects large enough to cause major regional damage are still out there, on orbits we have not yet determined, at positions in space we have not yet measured, following trajectories we cannot currently predict. They move through the darkness between the planets, invisible to all but the most dedicated searches, occasionally crossing the space near Earth without detection, occasionally coming very close, occasionally, as Chelyabinsk demonstrated, entering the atmosphere with no warning at all. The survey completion rate for the very largest objects is much better. For asteroids larger than 1 kilometer, objects capable of causing global catastrophic effects, potentially civilization-threatening impacts, we have found more than 90% of the estimated population. This is a genuine achievement of modern astronomy, the result of dedicated survey programs funded specifically to find and track large near-Earth objects. But the population below 1 kilometer, especially the objects near the 100-meter scale and smaller, remains only partly mapped. That is where much of the remaining danger lives. The Chelyabinsk impactor was approximately 19 meters across, too small to be detected by most asteroid surveys operating in 2013. The telescope apertures and survey cadences of the programs running at the time were optimized for larger objects. A 19-meter rock, dark and moving fast on a trajectory that happened to approach from the direction of the sun, making it effectively invisible from Earth-based telescopes looking away from solar glare, had essentially zero chance of detection before impact. The fact that it hit on the same day that asteroid 2012 DA14, a 130-meter asteroid that had been known and tracked for over a year, made its closest ever approach to Earth is a coincidence that required careful analysis to confirm. The two objects were on completely different trajectories, completely unrelated. Two asteroids, on the same day, one known and one unknown, one passing harmlessly by and one entering the atmosphere. The coincidence disturbed people in the asteroid science community not because the two events were related, but because it illustrated how little control we have over the timing of these discoveries. We found DA-14 because it was large enough to detect. We did not find the Chelyabinsk impactor because it was too small. Both of them arrived at Earth on the same February morning regardless of whether we were watching. Now let's talk about the ones that came closer. On September 4th, 2024, an asteroid designated 2024 RW1 entered Earth's atmosphere near the Philippines and disintegrated in a fireball. It had been discovered about 10 hours before impact. 10 hours. The object was only about 1 to 2 meters across, too small to survive atmospheric entry, too small to threaten a city, but large enough to reveal the system working in real time. Survey observations found it. Automatic warning systems predicted the impact. Astronomers tracked it until it disappeared into Earth's shadow less than an hour before entry. And even then, it was only the 9th asteroid ever discovered and tracked before impact. 9th. In the entire history of astronomical observation. Not because larger objects have not come close. Because we were not looking in the right places at the right times with the right instruments. One of the most unsettling close calls in modern asteroid tracking did not involve an impact. On March 5, 2009, an asteroid designated 2009 DD-45 passed Earth at a distance of approximately 72,000 kilometers, less than twice the altitude of geostationary satellites. An object approximately 30 to 40 meters across, roughly Chelyabinsk scale, passing inside the belt of communications satellites that modern civilization depends on. It had been discovered 2 days before closest approach. If 2009 DD-45 had struck Earth, it would have entered the atmosphere and exploded with the energy of a large nuclear weapon. Not planetary-scale destruction, not human extinction, but a city destroyer, potentially killing hundreds of thousands of people if it struck a populated area, capable of triggering a tsunami if it hit ocean near a coastline. It missed, by a distance that sounds large in human terms and is cosmically negligible. 2 days of warning. And the warning came not from a systematic survey, but from a single observatory that happened to spot it. Here is where the history of near misses reveals a pattern that the individual events obscure. In the early 1990s, NASA began the SpaceGuard program, the first systematic attempt to find and track near-Earth asteroids larger than 1 kilometer. The program expanded over subsequent decades. The Linear Survey, the Catalina Sky Survey, Pan-STARRS, Atlas, each generation more capable, covering more sky, reaching fainter objects. The result has been a dramatic increase in the rate of near-Earth object discoveries. In 1990, the total catalog of known near-Earth asteroids contained a few hundred objects. Today it contains more than 40,000. The survey programs are finding new ones at a rate of several hundred per month. What this means is not that there are more asteroids than there used to be. It means we are finding the ones that were always there. Every time the survey capabilities improve, more objects are found, and a corresponding number of previously unknown close approaches are recognized in retrospect. Objects that passed close to Earth years or decades ago, undetected at the time, now appearing in the catalog because their orbits have been reconstructed from new observations. The catalog of historical near misses grows with every improvement in survey capability. How many more close approaches are hidden in the part of the population we still have not cataloged? The asteroid that almost ended humanity is not a specific event in the past. It is a statistical certainty in the future. The impact rate for large objects, the frequency with which asteroids of various sizes strike Earth, is well established from the geological and lunar cratering record. Objects 100 meters across strike Earth approximately every few thousand years. Objects 1 kilometer across every few 100,000 years. Objects 10 kilometers across, the scale of the Chicxulub impactor that ended the non-avian dinosaurs, every 100 million years or so. The Chicxulub impactor struck approximately 66 million years ago. At the average recurrence interval, the next Chicxulub scale impact is expected sometime in the next tens of millions of years. That is not imminent by human standards. It is certain by geological standards. But the smaller threats are more frequent. Chelyabinsk-scale objects arrive far more often than extinction-scale objects. Larger city destroyers and regional devastation-scale asteroids are rarer, but many remain untracked, and that is the part of the risk that matters on human timescales. The planetary defense community expresses this risk in annual probability terms. For any given year, the probability that a large, untracked near-Earth asteroid strikes a populated area is small, much less than 1%. But integrated over decades and centuries, the cumulative probability is significant, and the distribution of impact sites is random. An untracked asteroid does not know to aim for an ocean or an uninhabited region. The risk is not the largest natural risk humanity faces. It is not something that should dominate every decision, but it is real in a way that is unusual. Unlike earthquakes, volcanoes, or hurricanes, an asteroid impact can sometimes be prevented if we see it early enough. In September 2022, humanity tested its first planetary defense system. The Double Asteroid Redirection Test, DART, was a NASA mission designed to test whether a spacecraft impact could change the orbit of an asteroid. The target was Dimorphos, the smaller member of the binary asteroid system Didymos, a rock approximately 160 meters across, orbiting its larger companion every 11 hours and 55 minutes. DART hit Dimorphos at approximately 6 kilometers per second on September 26, 2022. The orbital period of Dimorphos around Didymos changed by 33 minutes. Not an elimination of the asteroid, not a destruction, a nudge. A change in velocity of only a few millimeters per second, barely perceptible on a human scale, that, applied early enough, would be sufficient to divert an asteroid from an Earth-crossing trajectory. This is what planetary defense actually means. Not destroying an asteroid with a nuclear weapon, as movies have depicted. Pushing it gently, years or decades before impact. Changing its velocity by a tiny amount that compounds over time into a miss instead of a hit. DART worked. The concept is proven. The technology exists. The gap in the planetary defense chain is not the ability to deflect an asteroid we have found. It is the ability to find the ones we have not. The James Webb Space Telescope has found asteroids as a byproduct of its observations. Objects that crossed its field of view while it was looking at distant galaxies. JWST was not designed to be an asteroid survey instrument, but it has found them anyway. More importantly, NASA is developing the NEO Surveyor mission, a dedicated infrared space telescope specifically designed to find near-Earth objects, particularly the dark asteroids that absorb visible light and are difficult to detect from ground-based observatories. It is scheduled to launch no earlier than 2027 and is designed to accelerate the search for potentially hazardous objects larger than 140 meters. 140 meters is not a perfect threshold. Objects between 20 and 140 meters, the Chelyabinsk scale impactors, remain difficult to survey comprehensively. The population is large. The objects are small and dark. Full characterization of this population will require capabilities beyond NEO Surveyor. But NEO Surveyor represents a qualitative improvement in our ability to see what is out there to move the search for large hazardous objects from partial coverage towards something approaching a real planetary inventory. The people of Chelyabinsk had no warning because the instruments to provide warning did not exist for objects of that size in 2013. That gap is being addressed, slowly, with limited funding, against a population of objects that is large and partially dark and spread across the entire inner solar system. Here is the number that defines the problem. 4 near-Earth objects roughly 140 meters across or larger, the size range NASA uses for its main planetary defense survey goal. The estimated population is about 25,000. Less than half have been found. That means more than 10,000 large objects remain undiscovered. Their positions are unknown. Their velocities are unknown. Their trajectories are uncharacterized. They are out there right now, moving. Some of them on orbits that cross Earth's path. Some of them at distances and on trajectories that will not bring them close for thousands of years. Some of them, a small but non-zero number, on trajectories that could bring them close much sooner. We do not know which ones those are. We do not know because we have not looked carefully enough at the right parts of the sky with the right instruments for long enough. The people of Chelyabinsk looked up and saw a light brighter than the sun. They had 30 seconds. They had no warning. They were lucky that the object was small enough not to survive atmospheric entry intact. Lucky that it exploded at altitude rather than reaching the surface. Lucky that the geometry of the explosion directed most of the shock wave into unpopulated areas. Not everyone will be as lucky. The next Chelyabinsk could be larger, could arrive from a direction the surveys have not covered, could strike a city of 10 million instead of 1 million, could be a regional scale event rather than a local one. The probability on any given day is small. The probability over the next century is not negligible. The asteroid that almost ended humanity has not arrived yet. That sentence contains everything important about this problem. Not will not arrive. Has not arrived yet. The distinction is not semantic. It is the difference between a closed question and an open one, between a risk that has been addressed and a risk that continues. We have demonstrated that we can deflect an asteroid we have found. Dart proof that. We have not yet found all the asteroids we need to find. The survey is ongoing. The catalogs are growing. The instruments are improving. More near-Earth objects are being discovered every month than were known to exist in total a generation ago. And somewhere in the gap between what we have found and what is out there, in the part of the population that remains uncatalogued, in the dark rocks crossing silent space on trajectories we have not yet measured, is the asteroid that will define what kind of civilization we are. One that saw it coming, or one that didn't. The difference between those two outcomes is not physics. It is attention. It is the decision to look. It is the question of whether we choose to finish the map before the map becomes irrelevant. We have the tools. We are not yet finished. And the asteroids, indifferent to our schedules and our budgets and our competing priorities, continue to move through the dark on timescales that do not care whether we are ready.